All right, grade 9, so we are continuing on with our notes here. I'm just going to review the first part of the notes here. Didn't get this on video before, so I'm just going to go over this real quick. You should have these blanks filled out unless you're watching this video for the very first time. So these are the sort of final installment of the notes for chapter 5. We watched a video yesterday, and if you haven't watched this one yet, you need to watch this video. It's Crash Course Chemistry. It's on a video about the development of the periodic table and about Dmitry Mendeleev, the scientist behind that. So you can find that on MrMathWell.com. And here we go. That's the video. And here is the student notes right here. And these are the notes that we are filling in here today on the website. So this is what we did yesterday. The periodic table of elements is a chart that places all known elements in rows and columns. The elements are listed generally in order of atomic number. Atomic number is the number of protons in the nucleus of an atom. So we highlighted that on your periodic table you'll see, and here's a quick snapshot of the periodic table. Okay, so you will see that, and here's carbon over here. Let's zoom in. So there's carbon, we have a symbol, we have the name, and we have this number at the top. Okay, that is the atomic number, and that indicates the number of protons. Whoops, where were we here? The number of protons in the nucleus of the atom. Okay, so atoms of an element have slightly different masses, and they are called isotopes. So just like we in this room, we're all human, but we have different weights. Okay, we weigh different. We were to step on a scale, everybody would probably weigh just slightly a little bit different, and we would be like isotopes of the human race. We all have a little different mass, but we are still human. And so atoms or elements have atoms of that element. Some of them are a little bit heavier than others, and that comes because of the different number of protons. So in the nucleus, we have, for carbon, for example, we have protons in the nucleus. We also have neutrons, and for most carbon atoms, they have 6 protons and 6 neutrons. But some carbon atoms, for example, have 6 protons and 8 neutrons in the nucleus. And so this would be an isotope of carbon. Actually, both of these would be isotopes. This one is this one here is most common, okay? The one with 6 and 6. Now, we'll talk about this number at the bottom as well shortly. So we watched this in the video, we explained this yesterday, that according to the periodic law, elements are arranged in a repeated pattern of properties on the periodic table. So periodic, remember, that's the word that means it comes back around to kind of the same spot, so it kind of repeats itself. It's periodic. They used to call magazines and different things that came out every month or whatever, they used to call them periodicals, is what they used to call them, because they keep coming out over and over. That's a repeated pattern. And so the properties in the of elements of the periodic table are predictable, and they kind of flow one to the other in a logical way. And we did a little activity the other day as well about the puzzle activity, right? Where we tried to arrange, let's see if I can get that. We tried to arrange these pieces right here into a organizational structure where we could sort of see patterns. And so if you haven't done that one yet, you want to cut these pieces up and do that one. But we also related that to the periodic table. Okay. All right. So atomic mass is the mass of an atom, and that's found by counting the number of protons and neutrons in the nucleus. This is called the mass number. So the mass number is simply the sum of protons and neutrons in the nucleus. And there are electrons as well, but we don't count them in the mass because they are so small and they weigh very little. So they wouldn't contribute to the mass. It would sort of be like if I was taking the mass of myself and my hairs were the electrons, okay? So a single hair or even a collection of hair wouldn't really register on the scale. So that's kind of the same. Protons and neutrons would be like your body, and then the electrons would be like your hair. And especially my hair, there's not much of it, so it wouldn't weigh much at all. Okay, because of the isotopes, okay, so because there are sort of cousins of elements that have different masses, right? The average atomic mass is a decimal. So remember this number that I pointed to earlier, 12.011? That's the average atomic mass. So that considers all of the isotopes and their weights, and it divides them all up. It gets an average for all of those isotopes. An example would be this. If we had, 100 of these carbon-12 atoms, and this is the most common isotope, 6 protons, 6 neutrons. And if we had, 98 or 99 of them, and then we had like one of these carbon-14s, if we added them all up and divided by the total number, we would have our average atomic mass. This is not working very well. So the average atomic mass. Now, because most of them are 12 and only a few of them would be 14, the average would be pretty close to 12. And that's why we have 12.011. Now, if you add this up and divide it by 8, you don't get this number, but this was just an example. So it would be like most of them are carbon 12s, and then we have like a few other ones that are slightly different. Okay? So it would be like the average of our weights here in our room. If all of our weights was rounded to the nearest pound and we added up everybody's weight and divided by the number of people we have in here, we would get a decimal probably, right? So that's what's happening here. Okay. Atoms can gain or lose electrons, and the last thing we talked about in yesterday's lesson was electrons. They are negative particles that fly around the nucleus. You should know that by now. And when atoms gain or lose electrons, this makes the atoms either negatively charged or positively charged. So we talked yesterday about sodium. This is an atom of sodium over here on the left. And it has one lone electron that's kind of sticking out. It's on its outermost level. And this electron likes to kind of like leave, okay? It doesn't want to stick around. And so sodium has one less negative particle, and it's a charged positive ion now. Okay, so that's what sodium does. This electron likes to, it gets removed really easily. Chlorine, though, it has a lot of electrons kind of in its outer shell. It has one space that's open. And so for chlorine, instead of giving away electron, it likes to accept electron to complete that outer level. And so electrons like to jump into that spot, and that's why chlorine forms a negative ion. Okay? We can have positive ions or negative ions. All right, so continuing on with your notes here now, you probably have some blanks to fill in here. So let's talk about the categories of the periodic table there. Okay, so the question was, what makes atoms either want to gain or remove electrons? Let me just talk about that further. So if we have, remember this Bohr assignment, here's some of these I did for you. You're putting the protons in the middle, and the electrons are on the outside. The first ring has a capability of only holding 2 electrons. The second ring has a capability of holding 8. So let's just say here, for this neon one right here, you see this? It has a full first ring and a full second ring. That's perfect. The fluorine atom, if we were to draw fluorine, and I'll do this one for you here so we can understand, it has 9 protons, and it would have 9 electrons. One there, one there. Then in the next ring, it would have, what's 2 plus 7 gives you 9. So 1, 2, 3, 4, 5, 6, 7. Now, notice that there is room for one more electron here. Okay? And the reason why fluorine likes to become a fluorine negative ion is because it really wants an electron to fill its final spot. So it's like, it's like you're leaving for a tournament or something. You're playing basketball, you're leaving for a tournament, and you can only leave when all your vehicles are full. Okay? You can't leave with an empty vehicle. So you've got a van, and it's got, it's got 9 people in it, but it's a 10-seater van. And so you're waiting to go. You're looking for another person to come fill that spot so we can leave. Okay? It's kind of like that. It readily accepts an electron into that position. Over here, hydrogen, okay, or lithium, or sodium, they all have the same characteristic that they have one electron in the outermost ring. And so they're kind of like, well, you know what? I only have one here, so I could take up another one, but gee, I'm okay just to give one away. And electrons flow away from atoms really easily as well. And so these guys over here, really in these columns, they like to give away 1 electron or 2 electrons. Okay? Because they've got some extras. So that's how that works. Okay? All right? You're welcome. Okay, so let's get back to metals. Metals, these are elements on the left and middle of the periodic table. Okay, on the left and middle. So you'll want to fill in metals, I guess, as your blank there, right? These are the elements that have metallic properties. So those physical properties that we discussed, like luster and hardness and those kind of things, right? Metallic. They look like metals. They're shiny. They're brittle in some cases. So metallic properties. These are metals. The left side and the middle of the periodic table. Things like iron and magnesium and gold and sodium and stuff like that. The non-metals. Okay, this is now you'll flip your notes page there. The non-metals are elements on the upper right of the periodic table. These elements do not have metallic properties. Some are gases, others are solid and powdery. I don't have too many blanks for you there, but the non-metals, as I mentioned here, are kind of on this right here. These are the non-metals, okay? Well, maybe I won't include the hydrogen there, but these are the non-metals, kind of here, on this corner. These are the noble gases we talked about yesterday. Noble gases, they don't really like to react with anybody, but the non-metals are kind of over here, okay? And then the metals would basically be all of these. There's lots of metals on the table right here. And some of these guys in the middle are like, they're not sure. They kind of act like both. It depends. Okay, metals, non-metals. Okay, the metalloids would be the ones in the middle. These are elements that have metallic properties sometimes under certain conditions. Metalloids. Okay. They are situated on a staircase between the metals and non-metals. Being able to control these conditions makes them useful in electronics. So if you want them to act like metals and conduct electricity sometimes, that's great. We'll put them under certain circumstances they can do that. But you can also make them fairly insulative or non-reactive or non-conductive. And there's properties of both that can be used. So we're talking about like germanium, arsenic, antimony, those guys here. Okay, so the ones that are kind of roughly on the staircase, and it depends which chart you look at, but silicon would be one, okay? That kind of thing, silicon down here. Silicon is very, very important in the microchip technology industry, right?
Isn't it like the silicone chip?
Yeah, the silicon chip, right, silicon, that's right. So the silicon chip is very important in electronics. Okay, some names and symbols. Let's talk about the names and symbols. I've had some questions about that. Some names and symbols on the periodic table don't seem to match. They don't seem to match the name. This is because sometimes other languages are used for symbols. Sometimes other languages. So I actually I don't have on your notes here, but I just have this chart right here. I believe this is from your textbook. Yeah, page, I don't know what page it's at. Let's see. Can I see? Oh, page 161 in your textbook. And I thought, this is pretty great. I'll put this up on the board for you guys to see. But here's a listing of a bunch of the names, or even some of the names, the properties from other languages that give them their symbol. So oxygen is O, and oxygen, that's pretty easy to remember. Oxygen comes from the two words oxygenous, or acid forming. What are some of the other ones that are really weird? These ones are pretty logical. C, carbon, P, phosphorus, that sort of stuff. Metals, some of these metals. Okay, sodium, here we go. Sodium is Na. That's really weird, but it comes from the Latin word natrium. Potassium is K. That comes from the word kalium. We have a kalium potash mine right near our city here, right? It's just out of Regina towards the west.
It's pretty big.
Kalium mine, very big. Yeah. You bet. It's a solution mine. Anyways, you'll learn more about that in other math or science classes. What else? Iron. Iron is a little strange, right? Iron, how does Fe come about? That's from the Latin word ferrum. Ferrum. Silver, that's another one. Silver is argentum. Copper, I guess, is a little weird. It should be Co, maybe you think, but it's Cu, and that's from the Latin word cuprum. Gold is aurum. Au, Latin word again. Mercury, hydradrum. I never say that word, but hydradrum, liquid silver. And lead, PB is from the Latin term plumbum. Plumbum. Yeah, everybody's favorite Latin term there. So you don't have to memorize these, but getting to know these symbols are really important, okay? So sodium you should know is Na, potassium you should know is K, 'cause these are the strange ones, okay? So you take some time to memorize those. All right, back up to your notes here. Let's talk about the halogens, okay? The halogens. The halogens are the second farthest column to the right of the periodic table. So halogens, the second farthest column, up and down. These elements are very reactive, very reactive. All of them except one electron very easily, as I mentioned with fluorine. Fluorine is one of the halogens. And some are used in cleaning agents to kill bacteria and other living organisms in water, and some of those examples would be chlorine, bromine, and iodine. So our drinking water is chlorinated slightly to kill bacteria. You may have a hot tub or a pool or something. If you do, you would use either chlorine or bromine tablets again to kill bacteria that might grow in very hot water over time, and so on. Iodine used to, clean out a cut or something, put some iodine on a cut or something. Okay, and the halogens, where are they in the periodic table? Well, the halogens are right here. This is column 17. That's the halogens. Now, hydrogen, I don't like including hydrogen as a halogen, even though it sounds like it should be used there. But fluorine, chlorine, bromine, iodine, and astatine. Astatine is not really a chemical that we use. It's almost not even real. It's just sort of one of those mathematical predictions that Mendeleev made. And anyway, so astatine we don't use much. It's not useful for anything normal. Okay, fluorine, chlorine, bromine, iodine. You probably should remember those as the halogens. Any questions? Yeah.
When do we use plutonium?
When do we use plutonium? We don't use plutonium.
Travel back in time.
Yeah, to travel back in time if you have a DeLorean that does that. But yeah, we don't use plutonium. Yeah, the Libyan terrorists will be after us. And unfortunately, Doc Brown will die.
Yep.
So we don't want to use plutonium. It's very hard to get. It's very hard to get, especially in the 1950s.
And Marty will disappear.
Yeah, we're of course talking about Back to the Future. If anyone is totally lost. No, we won't use plutonium. No.
So astatine and plutonium are like things that we don't use? Or
Yeah.
How's that? What is that?
Well, did you mean polonium by astatine there? Because plutonium is number 94 Pu, and polonium is number 84 PO.
No, I meant plutonium.
Okay, yeah, no, we won't use plutonium. We're not going to mess around with uranium either,
What is it
radioactive
used for?
uranium.
Yeah. Like,
What is plutonium in the world?
Yeah, it's very radioactive. It's very unstable.
Explosives, right?
Yeah, explosives, nuclear things. Anyways, okay, electron energy levels. Now we know a little bit about this. We know a little bit about this from the Bohr diagrams. So let's complete our notes here. Electron energy levels in the Bohr model. That's the one with the rings that we did that little assignment on. Electrons occupy orbits surrounding the nucleus. An atom can be drawn with a nucleus where the protons and neutrons reside, as well as rings where the electrons would be placed. So here is a picture of the Bohr model of the atom. We have the nucleus in the middle, protons and neutrons in there, and electrons would be situated on the rings around the nucleus. And that is roughly what we understand the model to look like. We think it looks a little bit different than that, but this helps us to learn about a lot of the important aspects of the atom. So this is sort of what the atom is going to look like for us as we continue to research this. Okay? Now these are all the important terms and concepts from Chapter 5. I believe that we're kind of to the end of Chapter 5 now, and I do have some more questions for you to work on. So if you don't have these written down here already, these are the Chapter 5 questions, and these will all be due at a date to be announced. But write these questions down, and that's the end of our science lesson here today.